So let's look at how cross-validation does on a dataset that we're all familiar with. This is the modified NIST handwritten digit recognition dataset. We're going to start with, again, the same types of properties as we saw before. A feature for intensity on the x-axis, which we might call x1, and another one for symmetry for x2. And these are just linear terms. So if we wanted to draw just a standard hyperplane in 2 dimensions, we could be limited to that. And that'll draw probably a plane somewhat like this one. But we can see maybe there's some higher order effects here. We might be able to draw some type of nonlinear mapping that would bend the hyperplane a little bit. And the way we can do that is use a nonlinear mapping. Right? So if we constrict ourselves again to just using these 2 different feature sets of x1 and x2, we can consider squares or cross terms, like here are the second order terms. I'll just write that down. There could be third order terms as well, and all the way up to 5th order terms as exemplified up here. We could go higher than that, but probably we won't want to do that. So I'll just write 3rd order, 5th order terms. And we know that when we have more parameters, we're more likely to get overfitting. So we might want to decide, where along this axis of features might we want to stop. As we go more towards the right, we're going to get more power and representation in our model, but we could overfit. So where do we stop? So we can use validation to decide that. So what we can do is start with a low number of features on the left-hand side of this diagram and gradually increase this number of features to the right-hand side. So each of these is a different number of features. For example, 2 features, 3 features, 4 features, 5 features, 6 features. And we can plot the curves of validation error, testing error, and training error. These are all represented on this graph, so hopefully now you can identify which ones are which. Hopefully it's obvious with the more representation as we go from left to right here, we're going to get better and better training performance. So the cost with respect to training is going to go down. So that's our blue curve here. Our validation curve, as we already showed you before, is going to match our testing curve pretty well, but we know that validation is going to have an optimistic bias, so hopefully you've also understood that these are the labels that we'll get. We'll get a cost curve for validation. In fact, here we're using cross-validation, which we'll introduce in the next section, and the actual out-of-sample or test cost that happens on an unseen test set. And where we could choose is just basically because we don't have access to the testing costs, we would just see this validation curve here. We would choose one of these 2 values, right? And basically we would probably choose this one just based on the fact that it's doing the same level of performance as this with less features. You can see rather this actually does fairly well with respect to the actual test cost. It's much better than these other ones where the training cost is very low, but the validation cost seems to indicate it's overfitting. Anything around this area shows this. And you can see this actually in the real world on this data set. Without validation, when we use all 20 features, not surprisingly, we can fit the training data exactly. You can see this over here and over here, where there are perturbations to exactly get those particular points right. And you can see that the boundary is snaking to make sure that these are included while the x's are not. So something like that. But when we go for leave one out cross-validation, which we'll talk about on the next slide, you can see we might stop at 6 features, which we indicated to you on the last slide. And although we get a 0.8% training error, our test cost is significantly lower. So this is compared to this value here of 2.5%, now moved to 1.5%. And that may not seem like a whole lot of performance improvement. Remember, that's only 1% improvement. But we have to understand that in terms of error reduction, because the baseline performance is already very good here, we're reducing errors by 40%. That means the times in which you bump into a misclassified digit, it's going to be 40% less than in the first case on the left. So this is a big win for validation, showing us how many features we should use in our nonlinear mapping.